Hello and welcome. In this video, we're going to take a look at how the derivatives can help us to find the maximum and minimum values of a function. And this is going to open up the field of optimization, which is really all about finding out what kind of values will give us an absolute maximum value or an absolute minimum value of a function, depending on the application. So let's start off with the definition of minimum and maximum. And we have a couple different kinds. We can talk about a local minimum or a local maximum, as well as an absolute minimum or absolute maximum. The definitions are very close to one another. The local minimum means that at the point x equals c, f of c is less than or equal to f of x for all of the values nearby. So it's kind of like a little open interval around x. It's the lowest value of the function. Whereas an absolute minimum is the lowest of all of the values of f of x for all x in the domain. Same thing goes with a local maximum. It's just the biggest value of the function in a little local neighborhood. And an absolute maximum is the absolute largest value of the function over the entire domain. Now, with a couple of little visual representations here, you can see that a local maximum might not be an absolute maximum, but there's some other kind of interesting behavior too, where we can even find out that a function may not have an absolute maximum. In this first graph, you can see the domain of this function is from a to b, including the endpoints. And if we want to take a look for the absolute minimum, it would just be the absolute lowest value of the function, which would be down here. This would be the point where we would get an absolute minimum. So we would say that x equals a gives an absolute minimum, or that f of a is the absolute minimum value. Now, the absolute maximum value would occur at the highest point, so that would happen when x is equal to b. Now, there is also an additional maximum, but it's only a local maximum, and that would occur at this peak here. Maybe at some value of x equals c, this would be a local maximum. And at some value d, we can see that we would also get a local minimum. However, we can actually come up with an example that doesn't have any of these sort of behaviors. Take, for example, the graph of f of x equals 1 over x squared. Now, here the domain of this function is all of the values excluding 0. And if we try to find the absolute minimum value, we could be searching forever because we can continue to get lower as x goes to infinity. And we know by taking a look at the limit of this, as x goes to infinity, the limit of f of x is equal to 0, but we could never quite obtain that value. So we'd get to a certain point and say, well, I've gotten to a value of 0.001. That's pretty low, but you could go a little further and get 0.00001. Which of course is a little bit smaller. And no matter how far you go, you can always find a lower value. And that means that there is no value that is the lowest for the entire domain. There is no local min, and there is no absolute min. And that doesn't matter if we're going out to positive or negative infinity. What about an absolute maximum? Well, we have this other asymptotic behavior as x goes to 0, and our graph approaches infinity from both sides, which continues to get larger and larger and larger with, again, no bound. We can always go a bit larger than the last value we found for the maximum. And that means there's no local maximum and there's no absolute maximum. Now, in our quest to find the absolute maximum or absolute minimum, there is a very useful theorem that will guarantee the existence of an absolute maximum or absolute minimum. And this theorem has a very fitting name. It's called the extreme value theorem. And we need a couple criteria here for a function. We need it to be continuous and defined on a closed interval. If it's continuous over that closed interval from a to b, then we are guaranteed to have an absolute minimum and an absolute maximum in that interval. Again, with closed endpoints, meaning it actually could be the endpoint that could be the absolute minimum or maximum. Now, that's not to say that you can't have 2 points or more tie for an absolute maximum. If you have a function that just reaches the same highest point multiple times, then we would say that all of those points are tied for the absolute maximum. Now, the next trick is finding where we would get an absolute minimum or absolute maximum value. And luckily, that's where calculus is going to be helpful for us. We know that when we get to the top of a parabola that's opening downwards, we would have a horizontal tangent. And that's one kind of case where we could have a absolute maximum. In the case of a parabola opening upwards, same kind of idea. We would end up with a horizontal tangent at the bottom. And we can put that into a theorem. In fact, that is really the basis of Fermat's theorem. Fermat's theorem says that if f has a local maximum or a local minimum at some value x equals c, and if it is a differentiable function at c, then the derivative must equal 0. Which kind of makes sense, because if a function is differentiable, there's really only three options for the derivative. It's either positive, but that would mean increasing. Decreasing would be a negative value. Or case number 3, it has to be 0. Well, we can't get to a local maximum or a local minimum if we're still increasing or decreasing, so it kind of falls down to this. The derivative has to be equal to 0 at a local or even an absolute maximum or minimum value. But we could also have a maximum or minimum occur at a point on the function that is not differentiable. So we want to look for points where the derivative equals 0 or where the derivative is not defined. And we call those values critical numbers. A critical number of a function f is a number c in the domain of f, such that the derivative at c equals 0, or the function is not differentiable at c. F prime of c equals 0, that comes from Fermat's theorem, but of course there's one other case that could happen, and that's where we'd have something like a function having a sharp corner where the derivative does not exist, but we could still end up with a local minimum or maximum value. Not to say that every critical number will be a local minimum or maximum. There is the possibility where a function might just flatten out with a derivative of 0, but then continue to increase or decrease without giving us a minimum or maximum value. Now, as a little side note here, if you ever try to go and Google Fermat's theorem, you probably won't see this one come up as your first search result. He's got a much more famous theorem, Fermat's last theorem. And it's the kind of thing that is a great legacy of a mathematician, to leave a theorem that you're convinced works to the point where you will even say you can easily prove it works, and then not provide the proof and have mathematicians be stumped for a couple hundred years as to how to prove it. But I'll leave that for you to Google. It's kind of an interesting sort of mathematical historical problem that took forever to try to solve. Now, with all of these theorems and this idea of critical numbers, these are just the tools in the toolbox that allow us to find some sort of method to get absolute maximum and minimum values. We know that they're going to be available to be found if we have a function that's continuous on a closed interval, and we know that they're going to occur at critical numbers, with the exception of possibly an endpoint. Putting this all together, we come up with a method called the closed interval method. First, to use the closed interval method, we begin by saying that we need a function that is continuous on a closed interval from a to b. And that's from the extreme value theorem. We know the existence of absolute minimum and maximum values is there, and in order to find them, we'll start off by looking for all critical numbers of f somewhere in between a and b, and then we'll just simply evaluate f at every one of those critical numbers, and we'll see what the value of the function is. Then we're going to check out the endpoints, make sure not to forget about those. Sometimes the endpoints give us an absolute min or an absolute maximum value, and then we just look for the smallest of all of those values of f, and that's the absolute minimum. And we look for the largest values of all of those values of f, and that's the absolute maximum. So it's a fairly straightforward process. Let's try an example. In this example, we're going to take a look at a function that tells us the profit from selling x widgets or producing x widgets in a month. And p of x here is negative x cubed plus 80x squared plus 3500x minus 1200. And let's say that we can only make at most 100 widgets in a month. We want to find the maximum profit and also the amount of production that gives us that maximum profit. We just could call that the profit maximizing level of production. Well, using the idea that, well, a polynomial is a continuous function, and we know that we've got only an interval from 0 to 100 to work with, we can use the closed interval method. P of x is continuous on a closed interval from 0 to 100. So the first thing we'll start with is looking for critical numbers. To do that, we'll need the derivative. And once we have the derivative, we'll look for places where either the derivative is equal to 0 or is not defined. But because we're talking about a polynomial, we know polynomials are differentiable over the entire real number line. So it's certainly always going to be differential between 0 and 100. So there will be no type 2 critical numbers. In order to find type 1 critical numbers, we'll simply set p prime equal to 0. And when in doubt, of course, if you have a quadratic equal to 0, you can try out using the quadratic formula. However, it might actually be possible to factor. In this case, it actually is able to be factored. It's not exactly the easiest couple numbers to find, so using the quadratic formula would also suffice. And there are two critical numbers. We would see x is equal to 70 and x is equal to negative 50 over 3. But that critical number is not contained in the interval from 0 to 100, so that leaves us with only one critical number. Now, the second and third steps of the closed interval method is simply to evaluate this function, in this case profit, at the critical numbers as well as endpoints. So we'll start off by just making a little table of values for values of x, and we'll see that we need to look at the endpoints, 0 and 100, as well as the critical number, which is in this case 70. And we're just going to plug those values into our function and see which ends up being largest and smallest. And it's pretty straightforward to find out what the profit is when we only sell 0 widgets. We just have to take a look at the correct function. It means we're going to have to scroll back up to what was provided in the question. Plugging 0 back into the original function for profit will just give us negative 1,200. And that's basically just going to be the fixed cost, something that our business has to pay for whether or not we're going to sell and produce any widgets at all. Now let's try plugging in 70. I'm sure this is going to be a little bit more of a useful value. At a level of production of 70 widgets, we have 292,800. We'll assume this is in dollars maybe. And let's see what happens if we make the maximum level of production, a full 100 widgets. And you can see that we still make a substantial amount of profit, 148,800, but it's not nearly as good as only producing 70. So the maximum profit is 292,800, and the profit maximizing level of production is x equals 70 widgets. Now, of course, this was just a polynomial, so it makes finding the derivative quite easy, but that's really about the only part of this process that might end up being a little bit more challenging in other examples. Simply finding the derivative and then setting it equal to 0 to find type 1 critical numbers, or looking at the domain of the derivative and seeing where a function is not differentiable to get type 2 critical numbers. That gives you an idea of how we can use the derivative to find maximum and minimum values. And now, of course, we also have the difference between absolute and local minimum and maximum values. We're going to have some other techniques when we don't have a continuous function on a closed interval coming up. And most of those techniques are going to be used to find local minimum and maximum values. So stay tuned. Thanks for watching, and I'll see you in the next video.